Newton's third law states that for every action there is an equal and opposite reaction. That means that forces in nature always exist in pair. So if two objects interact, the force exerted on object 1 by object 2 is equal in magnitude but opposite in direction. So that's that equal and opposite. But it's opposite in direction of the force exerted on object 2 by object 1. So that means that no single forces, so isolated would be better, forces can exist. And in this case, when they're talking about the force pairs, they mean that the action force is equal in magnitude to the reaction force, but in the opposite direction. And in every case, the action and reaction forces act on different objects and must be of the same type. So that means that the force acting on a freely falling projectile is the force of the Earth on the projectile, and that magnitude of the force is mg. So if we were to draw that out, it would look like this. So we have an object that is freely falling, mg, and the reaction to this force is the force of the projectile on the Earth, and that would be going exactly opposite and would have a magnitude of negative mg. So if we were to draw that in what's called a free body diagram, we would use a point to represent that object, no matter if it's a TV or a couch or an anvil or what. We would use a point, and we would say that the force down is mg, and the force back up, we would want to be careful to try and make it the same length, just the opposite direction, would have a value of negative mg. And remember, by m, I mean the mass of the object, and g is acceleration due to gravity. Let's do another example. So if I have an object, let's say a book, sitting on a table. So here's my book, here's all of its pages, sitting on a table. Then the book is being pulled down with the force of gravity, which is equal to mass times gravity. And that means that the table is pushing back up. So if the book is being pulled down, the table's pushing back up with a force that is equal in magnitude but opposite in direction of that force of gravity. And that actually has a name. We call that the normal force. So F sub n is equal to the normal force. And therefore, that is equal to negative of the force of gravity, which is negative mg. Remember that gravity is equal to negative 9.8, that's a 0.8 meters per second squared. So if we plug that into the normal force equation, this negative times this negative would end up making the normal force a positive force. as you can see by the direction of the force arrow or force vector. So a couple things to note about the normal force. In this case, the normal force is equal to exactly the same magnitude but opposite sign of the gravitational force, because the book's surface is parallel to the table surface, which is also parallel to the Earth's surface. The normal force always acts perpendicular to the surface of the object. So let me erase this here. So for example, if I put that block on some kind of, or put that book on some kind of inclined plane, here's my book, pretend that it's not sliding down, it's just sitting there at rest, then we would still have that same force of gravity equal to mass times gravity. But our normal force this time would be acting in this direction, perpendicular to this surface of the inclined plane here. So our actual normal force would be directed perpendicular to that surface. So we have this sort of imaginary force opposite of the gravitational force directed upward, and we also have a component in this direction that would allow us to have our resultant be this normal force. So most often when we get problems like this, they give us the angle of that inclined plane, which allows us to get some information about how to calculate this normal force. But we will go into that later in the future. I just wanted to kind of give you the heads up that the normal force always acts perpendicular to the surface of the plane. So when we actually do the calculations, this theta here representing the angle at which the surface plane is inclined is also the same theta here, which is awesome, because then we can use SOHCAHTOA to solve for these different vector components, to solve for the final normal force. So what's important about vectors, that we've kind of been doing this, but just to be explicit, is that we have x and y components. So anything that has an angle like this normal force has x and y components. So our y component would be this force that is exactly equal and opposite of the gravitational force, and our x component would be a portion of that normal force.